know if this bodes very well for the assignment at the end of part 4, but the reason I'm a little late is because I was trying to kind of give you guys some hints, you know, how I like to do. They're fun. I don't know how many people are using my hints, but there are 4 problems at the end of part 4, and I was trying to give you some hints for those. My hint for you on Monday was your assignment, in addition to this, was to kind of double check to make sure we were all still on the same page with regard to calorimetry. Calorimetry basically is you have an isolated system and things are kind of swapping thermal energy, so we're going to pick up with that here, and we're going to do that in the lab tomorrow, etc. Forgot what I was going to say, so that's what I was saying. There is a review session for anybody who, I don't know if that's what you want to call it or not, but after this in the library, there will be something. I need to bug out about 4, so that still gives us an hour or so. Okay. So, as long as your system has a nice barrier and protects your system from the surroundings, what happens in the system stays in the system. So the change in thermal energy of your system is equal to 0, as long as it's isolated. That would be with regard to energy and matter. So, yeah, we talked about, earlier in part 4, we talked about kind of having a hot metal, putting it in room temperature water. The metal, cools down and the water heats up, okay? Kind of a change in thermal energy. We had a couple of terms happening in your system, and they were the change in thermal energy of the aluminum or the metal, the change in thermal energy of the water. Along those lines, I'm going to introduce something called the change in thermal energy of the reservoir, okay? And I'll try to kind of explain what that is. But oftentimes you have a chemical reaction that is endothermic or exothermic, okay? And actually that energy, the heat of that reaction, actually is going to be the Q of your reservoir. So as long as you have an isolated system, okay, we can set those changes that are occurring in your beaker, in your system, okay, to be equal to 0. So again, you have something giving up energy and something taking in energy. And actually it works out kind of nice because they are going to be equal in magnitude and opposite in sign. So that's kind of a nice thing. So the energy reservoir, the Q reservoir, what does that mean? And I already kind of said that's actually, we're going to turn that into the Q of your reaction. Okay, so there's something happening in your system. Okay, and we'll be kind of diving into why is energy released or why is energy absorbed when a chemical reaction occurs. But that is kind of how that works. So we have a couple of scenarios here. Okay, and I think I broke these up. So for instance, if you have a reaction occurring in your system, okay, and if your reaction is exothermic, and I'm going to draw a little picture here. Let's say it's happening in a beaker. All things happen in beakers, right? Let me change my color. So here is our system. It's isolated from the surroundings. It's nice and juicy. So actually, if this is water, that's actually going to be kind of our Q of our solution. But in there, we have some sort of reaction. Okay, and if your reaction is exothermic, we said that actually you're going to have a negative Q. So Q of reaction, so Q of RxN is going to be less than 0. Okay, if it's exothermic. And then here's the deal. You have the other thing you have in there, and I call it kind of your juice, is your liquid. Okay, if your reaction is exothermic, your solution is going to take in that energy and it's going to heat up. So it's endothermic. So the Q of your solution actually is going to be positive. Okay, so this is endothermic. What happens in the beaker stays in the beaker. So that's kind of what we have. So the second one of that is just the opposite of that. And these actually, that would make a great hot pack. Yesterday I was at Walmart and I'm hoping to do some like astronomy, still get out the telescope when it's cold, so I got some of those hot packs. So that'd be an exothermic reaction. There are also endothermic reactions. And so of course that would look like this. Okay, you have some sort of liquid in your beaker. You're going to have some sort of reaction, and if it is endothermic, okay, is going to absorb energy. Okay, and then the Q of your reaction or your reservoir is actually going to be positive. Okay, greater than 0. And then it is going to rob energy from your solution. Q of your solution here, okay, it's going to have to be exothermic. How does water be exothermic? Okay, basically it gives up its thermal energy. So if this is liquid water, you're going to see it cool down. So this Q is then actually going to be less than 0, and it's going to be giving up energy. Okay, so it's kind of a similar theme. It's not the metal in the water, it is the reaction in the water. Okay. So like I've been saying, you can kind of just go ahead and substitute. If you're like me, there's too many R's here. But instead of reservoir, I've gone ahead and changed it with reaction. And my favorite way to do to abbreviate reaction is RXN. And if it's isolated, okay, then we can, like I said, set those to equal in magnitude, opposite in sign. And it's a wonderful thing. So that's calorimetry. You're checking, you're watching, not really watching, but you're tracking the flow of energy. Sometimes just beware that on a test or on a homework problem, you can have more than one term. And actually on Friday's lecture, we'll be talking about definitely more than one term. All right, so we're going to look at an example. Yeah, so I didn't get this one. These just take longer than I think. Life's kind of like that. So I'll draw a picture up there kind of showing this chemical reaction. These sometimes you have to read a couple of times. Like I said, I would definitely encourage you, if it's a little fuzzy, to read your textbook. They do a good job. I try to do a good job. So let's kind of look at what's going on in the beaker. All right. So, I better change it to red so I can kind of. So, 0.5 grams of magnesium, 0.500 grams of magnesium, okay, is placed in a calorimeter. Do you see the word calorie in there? Calorimetry, not to be confused with a colorimeter, okay, which looks at color. It goes on to say that the HCl is an amount of 100 milliliters, and it gives the molarity. And we've talked about how we can go from that volume of 100 milliliters and the molarity of 1.00 moles per liter, we can get to moles of HCl, can't we? So I've kind of crammed underneath that reactant. So we have information about the two reactants. It also says that the density, and I'll kind of put it up above the HCl, it says the density of the HCl is equal to 1.02 grams per mil. So on to kind of drawing the beaker, which is going to be our system where those two reactants are going to dwell. Okay, so in goes my 0.500 grams of magnesium, and in goes my, I'll just put HCl here, because notice that we're given the volume and the density. We could get to mass using volume and density. All right. So those two are mixed together, and it goes ahead and tells you, wow, it goes up like 22.6 degrees? Dang. Okay. So that must be an exothermic reaction. Okay. So over here, I could say cube this reaction. It never hurts. I'll put the delta H of the reaction. I could put Q of reaction, probably better. It never hurts to say, does this make sense? So the fact that it's heating up means that actually it's going to be negative. It's going to be less than 0. It's an exothermic reaction. Okay, so I'll go ahead and put my two temperatures over there. Haven't gotten to the question yet. I'll put T sub I is equal to 22.2 degrees Celsius, and the final temperature after the reaction occurred is 44.8 degrees Celsius. So of course from this we can get delta T. Okay, and I'm going to go ahead and call that delta T of SOL, delta T of the solution. So based upon just what we've talked about just this lecture, an introduction to, over there kind of in the upper right I'm going to say what we talked about. Basically we have the Q of the system is equal to the change in thermal energy that the solution exhibits plus the change in thermal energy of the reaction. The reaction is giving up energy and the solution is taking in energy. Okay? So just to kind of remind you how we're going to work this problem, the Q of the solution, we are going to work using m C sub p delta T of the solution. So do you see with regard to change in thermal energy of the solution, we have the mass of the solution. Basically, we have the mass of the mass of the magnesium, we have the volume and the density of the HCl. So we have the mass of the solution. Specific heat of the solution, it says to go ahead and, if you read this neglect part, the last sentence, it says, go ahead and use the specific heat of that solution as that of water. Okay? Same as that of water. So I could add that up there. That's the last thing. So C says P of the solution. And I think it's been 4.18. We usually 4.184, but 4.18 joules per gram degrees Celsius. So that's going to be that term. Delta T of the water, we got it. Okay? It's from, or the delta T of the solution. So the bottom line then is if you know this, and it's kind of like when you work titrations problems, where you start with what you know the most about. We can come up with the change in thermal energy of the solution. And if your system is isolated then, like we were saying, and you're going to see this on my builds here in a minute, then the Q of the solution is equal to negative Q of the reaction. And Q of the reaction is what we're after. Whew, that's a lot. And there's more than just one last thing, but one other thing. You are going to get Q of this particular scenario. And notice that whenever you're given the final answer for a problem like this, they actually wanted an energy in terms of energy per mole of, and they'll tell you, in this case, per mole of magnesium. Okay, so we're going to go for the change in thermal energy of the water or the solution. We're going to set that equal to, we can set that equal to Q of the reaction. Then we just kind of need to normalize that per mole of magnesium. One more thing. There's always one more thing. When we work this, we need to find out which one we're going to run out of first. We've talked in here recently, in the last unit of material, that you cannot assume that all of your magnesium is going to be used up, and you cannot assume that all of your HCl is going to be used up. You need to find out which one you're going to run out of first, so we're going to knock that out too. All right, so on with a bunch of builds. So that's kind of the strategy, and that actually at the top there is the picture I would draw if I were working this problem. Okay, so we can knock out the Q of the solution using the mass. Remember, we have to account for that little mass of the magnesium and the big mass of the water. The specific heat, they told us go ahead and use the specific heat of water. Sometimes they'll give it to you in the problem. And of course, the initial and the final temperature of the water was given. Okay, so mass of the HCl solution using the density, 102 grams. So if we add that 102 grams to the 0.500 grams of magnesium, notice that, again, we don't do as much addition like this as we do multiplication and division. But since we're adding, we round according to decimals. The first term we know to the nearest ones, the mass of the HCl solution. The next term we know to the nearest, 0.001. So we have to round according to the nearest ones. So that's why that number is 103 grams. to get full credit on working these problems for your test on a week from tomorrow, you need to make sure that you round correctly. So that's going to be our mass term, and Q is equal to M C sub P delta T. So this is what the Q of the solution then is coming out to be. The mass of the solution that warmed up is 103 grams. The specific heat, they said go with the specific heat of water. The delta T we calculated between the final and the initial temperature is 22.6 degrees Celsius. When you work these, make sure that even though it's kind of like a plug and chug sort of thing, kind of physics does this a lot, make sure that you still include your units. So the beauty of that, I'll just kind of belabor this, is that if you include your units, grams in the mass cancel with grams in the specific heat. Degrees Celsius in specific heat cancel with degrees Celsius in delta T. And we're left with units of energy, which is what you ought to be left with. Sometimes students will ask me, do you really need this last term? And it depends. Probably not in this one. But it kind of brings down the numbers to being manageable. So we're not quite done yet. We're far from done. Sometimes students will miss the step where Q of the reaction is equal to negative Q of the solution. I need to see that somewhere, even though you are so close to going ahead and making that statement. You need to show me so you understand, so I know you understand, and you would want to show your boss that that's how you got that. So of course now Q of the reaction is equal to negative 9.74 kilojoules of energy. So that was how much energy was released given that quantity of magnesium and that amount of HCl. But we're still not done. And actually this step right here to identify what you're going to run out of first is going to be a step that you're going to need to do for your homework problems. Several of them that are due on Friday. So there's different ways to work this. I'm going to show you how I'm going to work it using kind of the have ratio and the need ratio. So I need to know what I'm going to run out of first. If your intuition is, I bet it's the magnesium, actually you're right, but you have to prove it. So with regard to moles of magnesium in that mass, that's a lot of M's, we use the molar mass of magnesium and say, that's 0.0206 moles of magnesium. Moles of HCl we can get from the volume and the molarity. Okay, so that third term up there is the molarity of the HCl. So you're going to see here in a minute, I'm going to do my have ratio, okay, of those two. And my need ratio comes from the stoichiometric coefficients. Okay, so my need ratio comes from the stoichiometric coefficients, the recipe. So we need 2 moles of HCl for every 1 mole of magnesium. Of course, that's 2 to 1. And what we have is 0.100 moles of HCl for every 0.0206 moles of magnesium. That's what we have. If you divide this out, you're going to see that we have 4.85 moles of HCl for every 1 mole of magnesium. We only need 2 moles of HCl for every 1 mole of magnesium. So your intuition was right, probably. You intuitively thought it was the magnesium. But unless you show it, you really can't finish the problem, unless they said it was the limited reactant. Okay, so yes, HCl is in excess, magnesium is in limited supply. So only after that can we finish off the problem and take that energy that was released in this scenario and normalize it per mole of magnesium. And that is the final answer. I like how this unit of material, a lot of things in chemistry do this, kind of keep building on itself. So you really kind of got to get into it on the ground level and sink your teeth into it and walk it on up. Okay, so that is the heat of that reaction. So yeah, I think I've got these first 3 problems kind of mapped out. So we'll kind of look at those and maybe briefly look at 39. And I think I will reserve the part gosh, part 7. Part 7's a doozy too. It's not very many slides, but the concepts presented in part 7 are very important with regard to calorimetry. So we'll reserve that for Friday. So let's take a look at these. These are due on Friday. And where did I? Looks like this one. Nope, that isn't it. Ignore that. Yes, all right. So there are 4 problems that are due. May take you a little bit of time, probably. Okay, so this is the first of 4 problems that are due on Friday. Okay, the stuff in green, okay, is like what you're given. So if you read it a couple times, it says that you're given 1.00 moles of the first reactant and 2.00 moles of the aluminum. So if you're like me, you're like, hey, that is one of those in chemistry we say we have the stoichiometric amounts needed. So, because the recipe calls for a 2-to-1 mole, and we have a 2-to-1 mole. So, like in the green I say over here, you can assume that everything's going to be used up. So this actually is one of the problems. You don't have to identify the limited reactant. Yay! It goes on, it says the thing's exothermic, and it gives a big negative delta H of the reaction. Okay, oops, sorry. I always do that. Come back here. Oops, that isn't what I wanted. So, all right. So notice it gives you the initial temperature of the reactants, 25 degrees Celsius. It also gives you a specific heat of the reactant, is 0.8 joules per gram degree Celsius. And if you read it a few times, and I know you probably haven't had a chance to read it, but it's basically wanting to know that when you take this certain mass of this Fe2O3 in the Al and you heat it up, or not heat up, sorry, allow it to react and it's going to heat up, is it going to reach a final temperature that is equal to or greater than the melting point temperature of iron, which they give as 1,530 degrees Celsius. So that is your question. So you're like, what the heck? So if we go on and kind of read it a few times, we can see that we're talking about the Q of the system. In a minute, you're going to see a beaker with the 2 reactants in it. You have a reaction occurring, and you have your mixture getting warmer. Okay, if it's isolated, then actually we're going to be able to say that however much warm our mixture gets, the change of thermal energy, the warming up of our mixture, will be equal to negative Q of the energy that's released. And of course, remember, they give you the energy per mole and 2 moles of that released up there. So notice that you already have the ability with the information given to quickly knock out the energy that must be released for this reaction. Because it said and I should have put 1.00, it said that you have 1.00 moles of Fe2O3 and 2.00 moles of Al. I said, and you probably could tell, which says in green, by inspection, that you're going to use up all of that stuff. So we can come up with the Q of the reaction by taking the moles given, which is that's what that is, times the energy released per mole. Okay, so bada boom, we have it. So meanwhile, this is where my reaction is occurring. How warm this stuff is going to get, because the energy released from the reaction can be anticipated by this. The Q of the mixture is equal to the mass of the mixture times the specific heat of the mixture times the change in temperature of the mixture. Notice if we kind of think this out, we actually can get to the mass of the mixture, but we're going to have to use those 1 and 2 moles respectively and their molar masses to get to the mass. So we need to get to the mass of this Fe2O3Al mixture, and we can do that from those moles and those molar mass. So that will be that term. Of course, the specific heat was given, 0.8 joules per gram degree Celsius. The delta T is what we're going to solve for, because notice we have the Q of the mixture. Why? Because we have the Q of the reaction, and they're related by equal in magnitude but opposite in sign. So in this relationship, the only variable we don't have is this. Now, I didn't finish this thought, but once you come up with delta T, you know T sub I is 25 degrees Celsius. Like we've done before, you've done in other homework, you can use delta T as T sub F minus T sub I to get to T sub F. Okay, so that's it. And what you'll do is to see if the final temperature, if it indeed exceeds or is at the melting point temperature of iron. Okay, the next one. Now, I've called this a reaction. It's really not a reaction, because by definition, a chemical reaction is said to occur if new substances are formed. It's more of a dissolving process. But sometimes when you dissolve stuff, it's exothermic, like what you're going to do tomorrow. And sometimes you dissolve stuff in water, and it's endothermic. So you can see already that this stuff actually warms up as you dissolve potassium hydroxide in water. The mass of the potassium hydroxide and the mass of the water are given. Again, they say, go with the specific heat of water. All right. So, let's see what else I got. They give you the initial and the final temperature. Of course, we can get delta T. Okay, so here again is a situation where it's not a reaction, but it really is the dissolving of potassium hydroxide is exothermic, and it's heating up your water. So energy is released by the dissolving process, and your water is benefiting from it, and you can see that by the increased temperature. Okay, so this actually is a case where, can you see, we can get to the Q of the solution. Because if you look over here, we have everything you need. We have the mass of the solution. Of course, don't forget to add these two together. The specific heat, they said go with water, and you can get the delta T from here. So now, in this case, once you have the Q of the solution, you can get to the Q of the reaction, which actually, that's what it's after. Okay, so you get the Q of the solution. Q of the reaction is equal magnitude but opposite in sign. Again, don't forget for full credit to write this down. All right, so you're almost done. Let's see, maybe this is where what did I say? This actually, I'm thinking you're going to need to, there's no limited reactant here. Sorry. Yeah, so you don't need to identify a limited supply reactant because it's not a reaction. But you're going to take that energy and divide it by the mass of the potassium hydroxide. A says it wants energy per mole, so of course you need one more term here, which is the molar mass of the KOH, and that's it. Honestly, I was thinking about B. Let me go back. I was thinking about B. I'm like, how could the precision of this measurement be improved without modifying the apparatus? I drew a blank. So if you come up with something, go ahead and write it down. What I'm most important or most curious about is your ability to answer A. All right, so the last one, I didn't get this one totally done. But again, we are, actually this is a chemical reaction. This is an oxidation reaction. We're combining zinc with, in acidic conditions. The mass of the zinc is given, the volume and the molarity of HCl that's providing the H+. This is a net ionic equation is given. And it tells you, oopsie, yep, that's where I ran out of. So I'll probably, during review session, try to finish knocking this out and make it available in case you're interested. But we can get delta T. It gives us the initial temperature and the final temperature. Again, this must be an exothermic process. Here, though, you do need to see which one you're going to run out of first, because after you get the energy, you're going to have to go ahead and normalize it based on mole of zinc. The thing about example 7.4, I looked it up in my office, and it's just saying use the specific heat of water as the specific heat of your solution, even though it's not pure water. The last one I don't have anything written down for, but let's just take a look at it. Again, it's a dissolving, not a reaction, which is kind of nice, so you don't have to identify a limited reactant. It says that, yeah, I was hoping it was one of these. it says that if you read it, actually, it's a decrease in temperature. So the Q of the reaction, or the dissolving process, is actually endothermic. And so you must have solution that's giving up thermal energy, okay, for this process to occur, which is the first question. The process must be endothermic. And actually, no calculations required for A. But there are calculations required for B. So the Q of the system is equal to the Q of the solution plus Q of the reaction is equal to 0. You have enough already to go ahead and knock out the Q of the solution, okay, and then set that equal to the negative Q of the reaction, and go ahead and normalize per mole of KCl, right? So yeah, those are good problems, 4 very good problems. And I will finish up. If I don't do it today, I'll do it sometime in my sleep. Okay, so let's go ahead and stop there and call that a day.